Howdy! This video is on equilibrium constants important to acid-base chemistry. Equilibrium constants enable us to determine the concentrations of products and reactants at equilibrium. One of the most powerful aspects of acid-base chemistry is that compounds can be rated based on the strength as an acid or strength as a base, and we do that using equilibrium constants. After watching this video, you should be able to write down the reactions corresponding to a particular Ka, Kb, Ksp, 1 over Ka, 1 over Kb, or 1 over Ksp. Given a reaction, you should be able to identify if its equilibrium constant is a Ka, Kb, Ksp, 1 over Ka, 1 over Kb, or 1 over Ksp. And you should be able to do problems involved using these equilibrium constants. So equilibrium constants, again, they enable us to determine the concentrations at equilibrium. Now, an acid dissociation constant is just an equilibrium constant. And acid dissociation means that we're starting with the acid as a reactant, and it's breaking apart into ions. Now, for a reaction that has a Ka as an equilibrium constant, you will always have hydrogen ion or hydronium ion as a product. Please remember, hydrogen ion and hydronium ion are the same thing. There's actually two equivalent ways of writing down reactions that correspond to Ka. We can just have the acid breaking apart into hydrogen ions and nitrate ions, or we can imagine the acid reacting with water, forming hydronium ion and nitrate ions. Now again, because the hydrogen ion and hydronium ion are exactly the same, and because pure solids, pure liquids do not appear in equilibrium expression, you notice that the equilibrium expressions for these two reactions are equivalent, and so these two reactions are equivalent. Now, I mentioned we can actually determine the relative strengths of acids and bases using equilibrium constants, and so the bigger the Ka, the stronger the acid. And so strong acids have Kas that are basically infinite. They're on the order of 10 to the 10th, 10 to the 9th, but for a strong acid, typically we assume that the Ka is infinite. For a weak acid, the Ka is going to be less than 1. And so in this table, we have a list of weak acids, and you notice that the Ka goes from 1 times 10 minus 1 down to 6.2 times 10 minus 10th. Now, this is not an exhaustive list. There's going to be some with larger Kas and some with smaller Kas. Now, Kb is also an equilibrium constant, so base dissociation constant, and so the base is reactant. It's breaking apart into ions, so sodium ions and hydroxide ions in this case. Now, just like for the acids, we can write the base dissociation in two ways. We can write it just as the base breaking up, or we can write it with a base reacting with water, forming hydroxide ions and ammonium ions. Now, for a Kb, the reaction corresponding with Kb, you will always have a hydroxide ion as product. Now, one thing that's a little confusing is that you can think about ammonia as your typical weak base. And so notice it does not contain any hydroxide, and the hydroxide is formed because the ammonia rips off the hydrogen ion, leaving the hydroxide ion. And so it's a little confusing. Even though this is not technically a base breaking apart, we still would say that the equilibrium constant for this reaction is a Kb, a base dissociation constant. Now here's a table of some bases. These are all weak bases. So strong bases, the Kb is going to be much, much greater than 1. We can treat it as infinite. For a weak base, the Kb is going to be less than 1. And so on this table, this is our strongest base. It's still just a weak base. Kw, which is the auto-ionization of water. Now, if you think about it, auto-ionization, it just means the water molecule is breaking apart into hydrogen ions and hydroxide ions. Now, if I write down the equilibrium expression, we have products or reactants, coefficients become exponents, pure solids, pure liquids do not appear, and so the liquid water doesn't appear, and we have Kw is just equal to the hydrogen ion concentration times hydroxide ion concentration. So again, Kw is just another equilibrium constant. And probably this is the most important equilibrium constant for aqueous acid-base chemistry. Remember, aqueous means that water is a solvent. Now, no matter what else is in the water, this equilibrium expression has to be followed. And so if you have an aqueous solution and your hydrogen ion concentration is 10 to minus 6, remember, if you have an aqueous solution, this equation has to be followed no matter what else is there. And so if we're given that we have a hydrogen ion concentration 10 to minus 6, we could be asked, what is the hydroxide ion concentration? And so we have Kw equals hydrogen ion concentration times hydroxide. Now we're looking for the hydroxide, so we solve for it. And so we divide both sides by the hydrogen ion concentration, And so we end up with hydrogen ion concentration equals Kw over the hydrogen ion concentration. Kw is 10 to the minus 14th. We're given that the hydrogen ion concentration is 10 to the minus 6. And so we get that hydroxide ion concentration is 10 to the minus 8th. And so in an aqueous solution, we're always able to determine the hydrogen concentration never given the hydroxide, or the hydroxide ion concentration given the hydrogen ion concentration, no matter what else is in solution. Now another Ekman constant is the solubility product. And so again, if we think about the name solubility product, we're going from an ionic solid and it's dissolving into aqueous ions. And again, if we write down the Ekman expression, products over reactants coefficients become exponents, pure solids, pure liquids do not appear. And so notice that the solid does not appear in the Ekman expression because again, pure solids, pure liquids do not appear. And so you need to be able to recognize when a reaction has an Ekman constant that's a KSP, Ka, Kb, Kw, or 1 over the inverse of these. You should also be able to write down the reactions that correspond to these different Ekman constants. And so HCN going to hydrogen ion plus Cn minus. So we have that H plus as a product. So that makes us think about Ka. And again, if I write down the Ekman expression, we have products over reactants, pure solids, pure liquids do not appear. Now, aqueous is not a pure liquid, and so it does appear in the Ekman expression. Now, you should remember that if we take the products, swap them with the reactants, so now we have H plus Cn minus going to HCN, the new Ekman constant is going to be 1 over the old Ekman constant. And so if the Ka of HCN is 6.2 times 10 minus 10, that is the Ekman constant for this reaction. Now we flipped it. And so the new Ekman constant is going to be 1 over the old Ekman constant. And so that gives us 1.6 times 10 to the 9th. Now, in recognizing the Ekman constants for reactions, often you're going to look at hydrogen ion or hydroxide ion or hydronium ion. And so notice that we have hydrogen ion as a product. So that makes us think of Ka. Here we have hydrogen ion as a reactant. So that makes us think of 1 over Ka. So what is the Ekman constant for the following? So HCl goes to hydrogen ion plus chloride ion. And so again, we see we have that hydrogen ion as a product. And so that must make us think about Ka. Now, if we look on the other side, it's going to be Ka of HCl. Now, hopefully you remember that HCl is a strong acid. So the Ka of HCl is going to be really, really large. Again, we can often treat it as infinite. Now, we could also write the reaction as HCl plus water going to the hydronium ion and chloride ion. And again, because hydrogen ion and hydronium ion are the same, and pure solids, pure liquids do not appear in the Ekman expression, these two reactions are exactly equivalent. They both have an Ekman constant of Ka. But again, please remember, hydrogen ion and hydronium ion are the same thing. And if you have a reaction that has an Ekman constant of Ka, you have to have either hydrogen ion or hydronium ion as a product. So what is the Ekman constant for this reaction? Notice that we got hydroxide as a reactant, but we also have hydrogen ion as a reactant. And so that makes us think about 1 over Kw. Remember, auto-ionization of water, you're going from water to the hydrogen ion plus hydroxide. Here we have the opposite, and so the Ekman constant is going to be 1 over the original Ekman constant. Now, Kw is 10 to the minus 14th, and so that means 1 over Kw is 10 to the 14th. And so the value of this Ekman constant is 10 to the 14th. So what is the Ekman constant for this reaction? And so remember, often we're going to look for hydrogen ion, hydronium ion, or hydroxide. So we see a hydronium ion here as a reactant. And so that's going to make us think about 1 over Ka. Remember, for Ka, you have to have hydrogen ion or hydronium ion as a product. Here we have hydronium ion as a reactant. So it's going to be 1 over Ka. Now, if we look on the other side, it's going to be 1 over Ka of nitric acid. Now, nitric acid is another strong acid, so its Ka is really large. And so 1 over Ka is going to be really small. And so Ka is very large. And again, 1 over Ka will be very small. And so the Ekman constant for this reaction is going to be very small. And so again, often when you're asked what is the Ekman constant for a reaction, look for the hydrogen ion, hydronium ion, or hydroxide. And again, we see hydronium ion as a reactant, so that makes us think about 1 over Ka. So what's the Ekman constant for this reaction? And so we have hydroxide ion. And so that makes us think about 1 over Kb. Remember, for KBs, the hydroxide will be a product. Here we have it as a reactant, and so it's going to be 1 over KB. Now, if we look on the other side of the hydroxide, we see we have ammonia, so it's 1 over KB of ammonia. Now, ammonia is a weak base, and so KB is going to be pretty small, and so 1 over KB is going to be large. So the Eckman constant for this reaction is going to be really pretty large. And again, hydroxide ion as a reactant makes us think about 1 over KB. Hydroxide ion as a product makes us think about KB. And so when trying to determine the Eckman constant for a reaction, you look for hydrogen ion, hydronium ion, or hydroxide ion. And again, remember, hydrogen ion and hydronium ion are the same thing. And so for the stop reaction, we see a hydroxide ion as a product. And so that makes us think, well, KB of ammonia. For the second one, we see hydroxide ion as a reactant. And so that's 1 over KB of ammonia. For this one, we see hydrogen ion as a product. So that makes us think about Ka. And so that would be Ka of nitric acid. Here we have hydronium ion as a product. And so again, that's going to be a Ka. And again, Ka of nitric acid. And so for these two reactions, they're exactly equivalent because hydronium ion and hydrogen ion are the same thing, and pure solids, pure liquids do not appear in Eckman expressions. For the next reaction, we see a hydrogen ion as a reactant, so that makes us think 1 over Ka. And then again, we see a hydronium ion as a reactant, so that makes us think 1 over Ka, and it's 1 over Ka of nitric acid. That's kind of interesting. These bottom 4 reactions are all related to the Ka of nitric acid. Now, polyprotic acid is one that has multiple ionizable protons, or multiple acidic protons. And that just means protons that can leave the structure, can be ripped off as hydrogen ions. And so this is phosphoric acid. It's got 3 acidic protons. Now, the number of acidic protons on a molecule does not affect its strength. Remember, the strength of an acid is determined by its Ka. The bigger the Ka, the stronger the acid. Now, the protons are actually removed in steps, not all at once. And so for each proton, you're going to have a different Ka. And so removing the first proton is going to be the easiest. Removing the second proton is going to be a little bit harder. And then removing the third proton is even harder. And so again, Ka1 is removing that first proton. Remember, a proton is just a hydrogen ion. Ka2 is removing the second one. And then Ka3 is removing the third one. And again, in a compound, Ka1 is always going to be greater than Ka2, which is always going to be greater than Ka3. And so here we have phosphoric acid. Removing that first hydrogen ion gives you dihydrogen phosphate. And so its Ka1 is 6.9 times 10 minus 3. Now, if we take the dihydrogen phosphate, we can remove the second proton, right? So we've already removed one hydrogen ion from phosphoric acid to get our dihydrogen phosphate. Now we're removing the second one, and so that's why this is a Ka2. Now we have hydrogen phosphate. Now for hydrogen phosphate, if we remove this hydrogen ion, that's the third acidic proton from phosphoric acid, and so that corresponds to Ka3. And so again, Ka1 is always greater than Ka2, which is always greater than Ka3. So what is the Eckman constant for this reaction? And so we have phosphoric acid going to 2 hydrogen ions plus hydrogen phosphate. And so if you notice, if we add these two reactions, we'll get the 2 hydrogens ions. The dihydrogen phosphate will cancel, leading with just the hydrogen phosphate. And you should remember that if you add reactions, you multiply the corresponding Eckman constants. And so the Eckman constant for this reaction is just going to be the 4.3 times 10 to the minus 2. When trying to determine the Eckman constant for a reaction, again, we look for hydrogen ion, hydronium ion, or hydroxide ion. Again, please remember the hydronium ion and the hydrogen ion are exactly the same. And so here we have hydrogen phosphate losing the hydrogen ion, going to the hydrogen ion plus the phosphate ion. And so this is going to be the Ka of hydrogen phosphate. Again, you have hydrogen ion as a product. Now the Ka of hydrogen phosphate is the Ka3 of phosphoric acid, right? So Eckham constant here you could say is the Ka of hydrogen phosphate. If you're looking for the numerical value, you'd actually look it up as Ka3 of phosphoric acid. For the next one, we have hydronamine as a reactant, so it makes us think about 1 over Ka. Look on this side, we have 1 over Ka of dihydrogen phosphate. Now, the Ka of dihydrogen phosphate is the Ka2 of phosphoric acid. And so the Eckham constant here is 1 over Ka2 of phosphoric acid. Now for this last one, we have hydronine again as reactant, so that's 1 over Ka. Now we have phosphoric acid, and so that's 1 over Ka of phosphoric acid, which is that's phosphorus acid. That's got 3 oxygen. And so that would be 1 over Ka1 of phosphorus acid. So when you have the O3, that's phosphorus. When you have the O4, that's phosphoric. And so again, when you're trying to determine the Eckham constant for reaction, you always look for the hydronine, hydronamine, or hydroxide ion. And so here we have phosphoric acid going to hydronine plus dihydrogen phosphate. And so its Ka1 is 6.9 times 10 minus 3. Now if we imagine it's reacting with hydroxide ion, so we have phosphoric acid plus hydroxide gives us water plus dihydrogen phosphate. The Eckham constant for this would be 1 over Kb of dihydrogen phosphate. And the Kb of dihydrogen phosphate equals the Kw over Ka. And so that means 1 over Kb is going to be equal to Ka over Kw. And so we have 6.9 times 10 minus 3 divided by 10 to the minus 14th, and that gives us 6.9 times 10 to the 11th. And so this is the Eckham constant for that right there. And so if we look at the reaction of hydroxide ion against phosphoric acid, dihydrogen phosphate, and hydrogen phosphate, we notice that we start with 6.9 times 10 to the 11th, and so that reaction is going to be far to the products. This one, it's not, the Eckham constant's not as large, and then the third one, it's even smaller. And so what this is showing us is that when the acid is reacting with hydroxide ion, it actually occurs in steps. And so we can actually look at it in terms of titration. And so we're starting with phosphoric acid, we're adding hydroxide ion, and first all the phosphoric acid reacts. And then the dihydrogen phosphate is what's left. And then that reacts, and so you have the hydrogen phosphate, and then that reacts, and then you end up with just the phosphate ion. Again, Ka1 is always greater than Ka2, it's always greater than Ka3. It's always harder to remove subsequent hydrogen ions. Now we could be asked, what is the hydrogen ion concentration of 0.01 molar per chloric acid? And so when you're doing this type of problem, you always have to figure out, what are you looking at? Is this an acid or a base? Is it a strong acid, weak acid, strong base, or weak base? And so hopefully you recognize HClO4 is on our list of strong acids. It's a strong acid, and so that means it completely dissociates, means that 100% of those molecules break apart into hydrogen ions and perchlorate ions. And so if we look at the table, again, if we start with 0.01 molar of this, then we end up with 0 of our perchloric acid, and we have 0.01 molar hydrogen ions and 0.01 molar perchlorate ions. And so it's a little confusing. If you have it a bottle labeled 0.01 molar perchloric acid, you would have none of these molecules because, again, it is a strong acid. It's on a list of 7 strong acids. We could also be asked, what's the hydroxide ion concentration in this solution? Now remember, this is an aqueous solution, so Kw has to equal hydrogen ion concentration times hydroxide ion concentration. So we're looking for the hydroxide ion concentration. So hydroxide ion concentration is equal to Kw of hydrogen ion concentration. Kw Kw is 10 to the minus 14th at 25 degrees Celsius, something you might want to remember. Our hydrogen concentration is given as 0.01, which is 10 to the minus 2, and so that means our hydroxide ion concentration will be 10 to the minus 12th. And so again, for aqueous solutions, given the hydrogen ion concentration, you can always calculate the hydroxide, and given the hydroxide ion concentration, you can always calculate the hydrogen ion concentration. And so here we're asked to calculate the hydrogen ion concentration of 0.01 molar acetic acid. And so remember, the COOH means it's organic acid, which is a weak acid. And so for weak acids, we always have to do an equilibrium problem. And so the reaction that we're doing the equilibrium problem for is going to be this breaking apart into hydrogen ions plus the acetate ion. Or you can imagine that we have this reacting with water, forming hydronium ion plus the acetate ion. The equilibrium constant for this is the Ka of acetic acid, which we should find in the table as 1.8 times 10 to the minus 5. And so we make our table, initial change equilibrium. We're assuming that initially we have 0 of these in a beaker, and we're starting with 0.01 molar acetic acid. Now when X of this dissolves, we'll get X of that plus X of that. Equilibrium is initial plus the change. Now, we could do it a couple different ways. If we want to solve it exactly, we can multiply this out. We can get this quadratic equation, and we can solve quadratic equations using this equation here. Remember, you always get 2 possible answers. One will not be possible, and so the 4.15 times 10 to the minus 4 is reasonable. The negative is not reasonable because you cannot have a negative concentration. So using the quadratic equation, we get 4.15 times 10 to the minus 4 hydrogen concentration. Now another way of doing it is, you remember, our Ka is really, really small. Equilibrium constants, products, or reactants. And so if you have really small K, that means you're going to have mostly reactant. And so probably X will be negligible compared to 0.01. Now, if we plug in, X and X for our hydronium ion concentration, acetate ion, we get X squared divided by 0.01. And so we multiply both sides by 0.01, we get that. We take the square root, we get X equals 4.24 times 10 to the minus 4th. Now notice our approximation was good. This is much smaller than 0.01. Also notice that when we did the quadratic equation, our answer was 0.15 times 10 to the minus 4th. And so our approximation gives us a really pretty close answer. Our approximation should be fine. And so when you're doing these types of problems, if you're asked about hydrogen ion concentration or hydroxide, pH or POH, first you have to ask yourself, what are you dealing with? Is it a strong acid or strong base? For strong acids and strong base, you do not need to do an equilibrium problem because they completely disassociate. Now, if you have a weak acid or weak base, you have to do an equilibrium problem. You have to know the equilibrium reaction involved. You have to be able to find the equilibrium constant, and then you do the equilibrium problem using the ICE table. Now we can look at another example. Here we have calculate the hydrogen concentration for 0.1 molar carbonic acid. And so again, we're going to look at the reaction. So carbonic acid breaks apart into hydrogen ions and bicarbonate. Remember, the first hydrogen is easy to remove. The second one is harder. So we're just going to worry about that first hydrogen initially. And so initially we have 0 hydrogen ions and bicarbonate ions in the water. We're going to have just the 0.1 molar of carbonic acid. When X of that reacts, we'll get X hydrogen ions and X of the bicarbonate. And so equilibrium is initial plus a change. Now our K is really pretty small, and so we should have mostly reactants. So X is going to be negligible compared to 0.1. And so we're assuming that X is much smaller than 0.1. Now we have our equilibrium expression, hydrogen concentration times bicarbonate divided by carbonic acid. So X times X gives us X squared divided by 0.1 equals our Ka of 4, that should be 4.5 times 10 to the minus 7th. And so we multiply both sides by 0.1. And so we get X squared equals 4.5 times 10 to the minus 8th. Take the square root, and we get 2.1 times 10 to the minus 4th. Now, if we think about our approximation, we said X was negligible compared to 0.1. It is. It's 3 orders of magnitude smaller, so our approximation was good. And so we get that the hydron concentration is 2.1 times 10 minus fourth. And so that's the concentrations at equilibrium. The bicarbonate ion concentration is 2.1, also 2.1 times 10 minus fourth. We could also ask, what is the hydroxide ion concentration of 0.01 molar potassium hydroxide? And so again, if we look at this, we should recognize it as a strong base. And so that means it's going to completely dissociate. And so all of our potassium hydroxides are going to form into potassium ions and hydroxide ions. Notice that for each one of these that breaks apart, you get one potassium ion and one hydroxide ion. And so our hydroxide ion concentration is 0.01. We could also ask, what is the hydron concentration of this solution? And so the solution's aqueous. And so remember, for aqueous solutions, no matter what else is in solution, the hydron concentration times hydroxide ion concentration has to equal our Kw. And so hydron concentration is equal to Kw over hydroxide ion concentration. And so Kw is 10 to the minus 14th divided by 10 to the minus 2. And so that gives us a hydron concentration of 10 to the minus 12th. And so here we're asked, what is the hydroxide ion concentration of this? And so this is a weak base. It's got a Kb of 1.7 times 10 minus 9th. And so again, for strong acids and strong bases, we do not need to do an equilibrium problem. For weak acids and weak bases like this one, we do have to do an equilibrium problem. And so we write down the reaction. Now initially there's 0 of these in our beaker. We're just starting with the 0.1 molar of that weak base. Remember, when that breaks apart, we get one of those and one of those. Equilibrium's initial plus change. Now our Kb is really small, and so most likely x is negligible compared to 0.1. And so we have that. Now we have the equilibrium expression. We have the products of reactants, coefficients become exponents, pure solids, pure liquids do not appear. So that's why we don't have to worry about the water. And so x times x gives us x squared divided by 0.1 equals our Kb of 1.7 times 10 minus 9th. And so we can multiply this out. That gives us 1.7 times 10 minus 10th. If we take the square root, we get x equals 1.3 times 10 minus 5. Now, if we think about our approximation, we said that x was going to be negligible compared to 0.1, and it is, so our approximation was good. And so at equilibrium, we'll have 1.3 times 10 minus 5 of the hydroxide ion concentration, 1.3 times 10 minus 5 of this, and about 0.1 of our initial weak base. Now again, we could be asked, what's the hydron concentration? And again, for all aqueous solutions, no matter what else is in solution, the hydron concentration times hydroxide has to equal to Kw. And so hydron concentration equals Kw over hydroxide. And again, you should remember that Kw is 1 times 10 minus 14th. And so 1 times 10 minus 14th divided by 1.3 times 10 minus 5 gives us 7.7 times 10 to the minus 10th. And so you should be able to determine if a reaction is a Ka, Kb, Ksp, 1 over Ka, 1 over Kb, 1 over Ksp. And again, the way of doing that is looking for the hydrogen ion, hydroxide ion, or hydronium ion species. And so again, if you see a hydroxide ion as a product, think Kb. If you see it as a reactant, think 1 over Kb. If you see hydrogen ion or hydronium ion as a product, think Ka. If you see those as reactants, think 1 over Ka. I hope that helps.